So this test is 6.1 through 6.3, 3 parts. Again, like 8 to 10 multiple choice to start, mainly conceptual. Anything multiple choice that would be mathematical would be very straightforward math. For example, an object doubles or triples a parameter, whether that be the height of the object, the velocity, and then I might ask you what happens as a result to the potential or kinetic energy. So if you think back to the video a moment ago, the guy at the top that jumped off had probably like triple the mass of the kid that was on there. So we saw how much higher the little kid went because of that ratio of the mass of, say, 3 to 1. Well, what happens if you double the velocity? Then what happens to the kinetic energy? What happens when you change the height? What happens to the potential energy? So it changes as a function of those parameters. So multiple choice-wise, you should definitely expect things like that. Also, basic math things such as, an object is launched from a cliff or falls from a certain height. Let's say the object starts with 100 joules of potential energy. And along the way, it undergoes air resistance. And air resistance causes it to dissipate 30 joules of energy. Determine the kinetic energy before it hits the ground. I mean, it's 100 to start. You lose 30 along the way. What kind of energy at the end? It's all kinetic. So you have 100 minus 30, you get 70 joules of energy. So understanding the concept of balance of energy, conservation of energy. Understanding the definition of work in the context of conceptual questions. When is work done? When is work done? When an object moves. Again, it's got to move and it needs what else? It's moving under what? What causes it to move? A force. Remember, it's F, D, cosine theta. That's our definition of work. It's got to be moving, there's got to be a force applied. What if there was a question on your problem set, it had a catcher, and the catcher was catching the ball, and it talked about the work done. So, I told the other class, there's really 2 correct answers, depending on the way you interpret it. If I'm a catcher, right? I was a catcher in high school baseball. You throw a fastball in, I catch the ball. Either my glove could come back a little bit, theoretically, if it was thrown hard enough, or I catch the ball and my hand doesn't move. If my hand doesn't move as I catch it, there's no distance traveled, right? So technically, there's like no work done, you could say. It's a bit weird, but even though you'd say if it didn't move, but it's got to move for work to be done. So imagine your glove moves back a little bit, right? Well, which way was the object moving was moving this way. Which way are you applying a force to cause it to stop? The other way. So the object and your glove move this way. Your force you're pushing is that way. So what kind of work do you do on the object? Negative work, because they're in opposite directions. Remember, the directional is what matters. If I push an object to the right, and at the same time I apply push, the object is moving to the right. If that's the case, then you're doing positive work. If work and direction are in the same, or distance are in the same direction, you're doing positive work. God bless you. It's like the example where the iPad's at rest. If I push it this way and it moves this way, I'm doing positive work. I'm giving it energy. But ready? I push it and I let go. Why did it stop? Friction. Friction is pushing back. It's doing negative work. Again, it's moving this way. Friction is pushing this way. What's the angle? 180. And the cosine of 180 is negative 1. That's why friction does work. And it does specifically negative work. It causes the object to lose energy. Mike, could you crack that window? Just open as far as possible. Now, we also want to consider the fact that with these problems, in addition to the work kinetic energy, in addition to work, we have what's called the work kinetic energy theorem. Okay, the work kinetic energy theorem. What did that tell us? The work kinetic, this is one of the 2 main theorems we're going to use. I'll give you the starting point. That was the starting point. What does the work kinetic energy theorem tell us? Physically, what does it tell us? What's happening? Bernadette? It's a change in kinetic energy. What is that caused by? Why is the kinetic energy of the object changing? Close, you're on the right track. A force is applied. The force can be constant, it doesn't have to be changing. A force causes work, doesn't it? A force causes work.
Is it when the potential energy increases the kinetic energy?
For vertical motion and with conservation with objects moving up and down. This is the work kinetic energy theorem, which is horizontal motion. This was back in 6.2. Okay, back in 6.3, that's what we were talking about, where when it loses potential, it gains kinetic. You're right. But in 6.2, I'm specifically talking about work kinetic energy theorem. So again, when I do work on an object, it causes a change in kinetic energy. If I apply a certain force, say 25 newtons, over a distance of 4 meters, 25 times 4 is 100 joules. That means I'm giving it 100 joules of energy by the work I'm doing. So at the end, it's got to have more energy than it started with. And there's my definition. Final minus initial. So give me a number between 0 and 50. 25? So let's say that the energy of the object started with 25 joules. How much will it finish with? What's the final energy going to be? If it started with 25 joules, you did this much work on it, what's it going to finish with? Guys, just fill in the blank. 100 equals x minus 25. What should go in this blank? 125. So again, if the object, ready? Here's the iPad. It's already moving. It has an energy level of 25 joules. I come by while it's moving and give it another 100 joules of energy. Well, it had 25. I did 100 joules of work on it. So now it has, at the end, 125 joules of energy. So this is the most basic way of interpreting the work kinetic energy theorem. And then we can go into a lot more depth. We could say, well, work is change in kinetic energy. So we could write this if we wanted to. Oops. If we were given enough information. If, say, we were given the mass of the object, the initial velocity, the total work done, 75 joules, whatever, you could find the final velocity. Okay, so or maybe I give you the final velocity, the initial velocity, and the mass. And I say, how much work is done on this object to cause it to accelerate from a velocity of 10 meters per second to 30 meters per second if its mass is 7 kilograms? See, as I spoke, I pointed out where that stuff would go. To accelerate an object from 7 meters per second to 10 meters per second, whatever number I just chose, if the mass is, say, 15 kilograms, that goes there. You calculate it and you can solve for work. Now, that's solving for work. If I give you a force due to friction, if I give you and say the force of friction is equal to some number, figure out the distance traveled, well now you would plug in the formula for work. And then this would all carry down. You have the force applied from friction, you can determine the amount of distance traveled. Or you have the force applied by a push, you can determine the distance traveled. Or maybe you have the distance traveled and your goal is to figure out how much force do you need to move at a distance of 12 meters if the velocity changes and the mass is given. So this is all given, and maybe you're finding the force necessary to cause it to move a certain distance. So the work kinetic energy theorem starts here. That's the most basic way to interpret it, and that's the way it's written on your formula sheet. On your formula sheet, I hope you know this by now after doing all this work, this is how it's shown. You need to replace this with W equals KEF minus KEI. Okay, forget the 100 for a minute, make believe it's still W. And then further replacing this and this with these two. And if you need to, you could also replace work with this. So in the end, you get FD cosine theta equals 1/2 mvf squared minus 1/2 mvi squared. So that could be the work kinetic energy theorem. It depends on what you're given. That's why you need to know your units. If you're given the amount of work done in joules, that number goes right here. And you don't need to replace that value W with this formula at all. If I give you the amount of work done in joules. Is that clear? If you're given, say, the distance in meters, and you want to find the force, well, then you need to recognize you're given that value, D, right there, and your goal is to find this value over here, the force. Okay? It's the first main concept of this entire chapter. What was the second main concept that you started? You started we did it the last few days, but you also did it on your lab yesterday. What is that idea or theorem? What would you call it? What was 6.3 all about? Potential, yeah, it was involved. Springs were involved. But what was the whole thing called? Conservation of mechanical or conservation of total energy. The idea was conservation. And this is what we had. Okay? Which tells us that the amount of energy you start a problem with has to be the amount of energy at any instant in time. So if the problem starts from a cliff and it's on the way down and it ends maybe 20 meters before the end of the ground, call that ground level. So here's the problem. The object starts here. It's launched with some initial velocity. It's falling down. And the goal is to figure out the velocity at an instant when it's 10 meters above the ground. Okay, this is conservation of energy. If it was 10 meters above the ground, what we could do is we could call this level the zero potential energy line. And as a result, what's my actual height from start to finish? 20, really. Okay? Again, I personally would call the ground level wherever the problem finishes, or wherever the problem starts, depending upon if it's thrown up or down. If you throw an object up and you're trying to find out what the max height gets to, yeah, you start on the ground. That's normal. If you throw it down, you start or you end wherever the problem ends. That's where your P equals 0. So I could literally reverse this problem and do the opposite. What kind of energy would I have in the beginning for this problem? It's thrown from a cliff. Potential? Kinetic. Why did you say kinetic? It's thrown. As it's falling, what is happening? What kind of energy is it losing when it falls? Potential. And what is it gaining? Kinetic. Okay, at the end, when it gets to this location right here, which I've called ground level, how much potential energy is left? Yeah, because I'm calling it ground level. So this is all kinetic at the end. So my equation up here becomes okay? PEI plus KEI equals KEF. So is this the same equation? Is this going to be the same thing for every problem? What is it depending upon? The conditions, the situation, what's given. But this will always be the same to start, right? That's my conservation theorem. How about this one? What if there's energy loss along the way? Where does that energy loss go? We kind of talked about this when Caroline was doing that quick demo there. Where does the energy loss get taken into account if there's energy loss due to friction? If it's rotating or if there's air resistance, but physically in the equation I'm saying, where does it come into play? The left side or the right side? Yeah. Again, remember, if you lose energy, we put an absolute value over here, and I've been calling that Q or W friction. It's just the amount of energy lost. If you need to break up work into F, D, cos theta, it's probably going to be with the work kinetic energy theorem or another example. With projectile motion, I'm going to give you a hint with these problems. I'm going to probably tell you how much energy is lost due to friction. So let's say you lose 30 joules of energy due to friction. It simply means that you put a 30 here at the end. And then everything else carries down. All your formulas all carry down. Okay, the 30 goes in for the amount of energy lost. Everything else can be easily calculated given the other parameters. So if you want the initial height of, we have that, is 20 meters. We have the initial height. We, let's say, have the mass, because you would need the mass. Now that the 30 is here, we can't cancel mass. If this 30 was not here, make believe this is covered up, you could cancel all your masses. But we'd have to be given the mass. Okay, so you're given the mass, you're given the height. Let's say you're given the initial velocity you throw it with is 5 meters per second, very lightly. You're trying to figure out what's the final velocity, or what's the velocity at this instant. Why do I call this instant the final part? Because that's the end of my problem. Sure, it continues and eventually hits the ground. But the problem is insisting on asking us, what is the velocity here? So I'm calling that final velocity because that's the end of the problem. And the goal would be to solve for VF. Again, given m is here, given the initial velocity, given the initial height of 20 meters, again, the height above where it started to where it ends, 20 meters. You could solve for VF. Now, yeah?
Will it be required to draw a diagram?
Again, I'm going to write in the problem, draw a diagram and label the energies along the way. If you could do it and you get all of it right without a diagram at all and it's perfectly right, I'd probably still give you full credit. But if you get a lot wrong and there's no diagram, you're not going to get much partial credit at all. So the diagram is like 1 out of 5 points off the bat. So I would probably draw a diagram to start. And I would do it the way I did, where you label the type of energy at each instant and label the PE equals 0 line. Okay? Follow up. Ready? How does it change? How does it change if we throw it from the ground up to the top now? Starts with no potential. So new diagram, same scenario, launched up now. Let's say that it reaches the cliff, and when it reaches the cliff, it's still moving. It's still moving, okay? It's eventually going to keep going over, ending up on a ledge somewhere. But we're trying to figure out right here at this instant when it reaches the cliff. So in the beginning, the first comment Angie just said is there's no potential. Why not? Why is there no potential to start this problem? Why not? Why not? It's at ground level. This is my P equals 0 line. Again, in this case, it's where I start the problem. In the last case, it was where the problem ended. Whereas here, it's where the problem begins. Okay, this is going upward. So it's got kinetic energy because you're launching it. When it gets to a certain height, at the end, it's got to have potential. And because I said it was still moving, if it's still moving when it reaches the top, it still has kinetic there. Now, please remember, I'm talking about things that are thrown at angles. What about this scenario? And this is the one that you're probably more familiar with. An object is launched straight up. It gets to the top, it stops, and it falls straight back down. Give me something about that. Give me energies. It's launched up. So what does that tell you off the bat?
It gains potential.
It's gaining potential because it's launched upward. Okay, so it's got to have some potential at the end because it's gaining it. What did it start with? Kinetic, because it's thrown or launched upward. How about along the way? What kind of energy does it have? Both. So here, follow me please. Ready? All kinetic, losing kinetic while gaining potential at the halfway point. Be more precise. It's equal. It has equal amounts of kinetic and potential energy at the midpoint. And then, suddenly now there's more potential, less kinetic, much less kinetic. How much kinetic at the top? None. It stops. How about on the way down? What happens? Yeah. It starts with the potential. It loses potential, gains kinetic, half and half. More kinetic, all kinetic, no potential at the end. Any questions on this? This is exactly analogous, to the half pipe example with the skater back and forth. This is also the same as this, with the skater going down the ramp. All potential, all kinetic. This is also the same as the pendulum problem. All potential here, when it reaches the bottom of its path, all kinetic. Again, I'm considering this to be the ground level for the pendulum problem. This is the ground level for the skater problem. This is the ground level for the ramp problem. These are all the same. They're literally all the same. KE equals PE. That's it. That's a one instance where that happens, right? But it happens a lot. So what do you think you could expect mathematically on this test? Probably something with regards to just a vertical motion problem or a problem that involves a transfer of simply potential to kinetic. Okay, why would I ask you that? Most likely because it's a problem where you're not also given mass. If you're not given mass, what can you automatically infer or almost assume? Yeah, mass will probably cancel somewhere along the way. Okay, somewhere along the way. So the whole test is work kinetic energy theorem, conservation of energy. Those two things are really the whole test. But you need to be able to determine the work done in general, FD cosine theta. If it's at an angle, put the angle in. For example, I did this in class. You've got a mine shaft. The object is being pulled. It hits a pulley, and then it redirects it. The force applied is here. Somebody's pulling on this cable, yet the object is moving up and down like that. It's moving vertically. So there's theta. Remember, the angle is always the angle between the applied force and the direction of motion. Motion is up. The applied force is at an angle. That's theta. This is similar to this problem. Ready? You got a floor. Here's an object. You apply a force at an angle of theta. The motion is horizontal. So there's theta. See how these are different thetas? One is given between the force and the horizontal. One is given between the force and the vertical. But remember, theta is the angle between the direction of motion and the force. the direction of motion, and the force. That's our theta value. Okay, and to find the work done, in this case, it's F d cos theta. In this case, it'd be the force of tension. Sometimes it could be, you could call it a push, a pull. You could say it's the force of gravity acting on it. There was a problem in your problem set, actually, or homework about this. An object is launched up. On the way up, what kind of work is gravity doing? Which way does gravity pull? But isn't it moving up, we just said? So it's pulling down gravity, but it's moving up. So what kind of work? Negative work, which is why it's slowing down. And then it gets to the top, what happens? And then it starts to move which way? And isn't the force of gravity down? So when it's on the way down, what kind of work is it doing? And therefore, its speed is increasing. When positive work is done, speed increases. Maybe write that down. When negative work is done, speed decreases. This all goes back to the work kinetic energy theorem also. Because kinetic energy has to do with speed. I keep talking about speed and work because work and kinetic energy are related to one another. Was there a question or two or something you wanted to ask? Maybe something from the problem set that you really struggled with you wanted to ask about? I've really covered all the ideas of this test already. Now it's just practice problems, right? But I want to ask you, were there questions you had? Yeah.
Question to catch your problem set. I know you just explained that. So is the answer negative?
It depended upon your reasoning. If you said that the catcher's glove did move because it moved this way and the force you push is that way, then the answer would be negative work. If you said that the catcher's glove did not move, zero distance, it's zero work. But it was not positive work. The pitcher, right, Mike? The pitcher, he gives the ball velocity. He accelerates it. The pitcher does positive work on the ball. The catcher slows it down, thus doing negative work. Okay? So anything that slows something down, what kind of work does it do? Negative work. So that could be friction. That could be you catching an object. That could be a linebacker slowing down a running back as he tries to run through him. Anytime you slow something down, negative work. Speed it up, positive work. Where does that come from again? It comes from this, right here. If you do positive work, you gain kinetic energy. You speed it up. If you do negative work, you lose kinetic energy. You slow it down. It's all back to the work kinetic energy theorem here. This is used for horizontal problems not involving elastic energy or potential energy due to height. Elastic energy. Talk about that. Equation 1/2 kx squared. How do you know what k is in a problem? How do you automatically identify k in a problem? What are the key factors? It's the spring constant, good. What else is an indicating factor? That could be the word it's used. But there's something else about it that tells you that it's the K value. Thank you. It's units. Anybody remember them? Newton per meter. Very good. The amount of newtons of force it takes to stretch it a meter. That's the K value. What is X? What is X? It's not horizontal displacement. Remember, here we're using D for distance for the work done. What is X? John? Jack?
I was going to say, was it distance?
But be more specific.
Distance traveled? Or distance
It's
pulled?
the spring.
Pulled.
Yeah. Pulled or compressed. Okay, this is the compressed distance or stretched distance. So if a spring starts at 20 centimeters, you compress it to 14. What's X? Starts at 20, compress it to 14. 6 centimeters. Negative or positive, doesn't matter. Why not? You're squaring X, aren't you? Okay, it just gains energy in general there. It gains energy. So that's a problem like this. It's compressed to a distance like that. Well, how do I find the actual X value? This is the X value here. Okay, the distance between center to center, where it started, where it ended, from center to center, or front to front, or back to back. Doesn't matter. As long as you are consistent where you pick the point on the object. Other questions you have? No questions at all in the problem set? There were none that tripped you up along the way? I mean, a lot of you submit electronically, so you have it on your iPad. Those submit hard copies, I know it's tough unless you take a picture, which was a recommendation I did make. How could a spring be involved? Let's say there's a spring here. So you've got like a little cannon. And a cannon, I know it uses combustion, but let's say it acts as a spring. It's like a catapult, okay? You release the catapult, it gets launched. So, where is the energy currently being stored? It's stored in elastic energy. The problem does not start until you pull the pin and it gets launched. So it doesn't have velocity to start. The only time you have velocity to start is when you give it velocity. Remember, it's not moving right now. Before the spring expands, it's not moving. So there's no velocity. Sure, once the spring expands fully and the object is now launched and maybe like it's here along the way, on its way up to a certain height, yeah, then it's got velocity. It's got velocity here once the spring expands and releases it. But while it's on the spring, there's no velocity. When it reaches the top of the cliff, let's say it's not moving anymore. It just makes it to the cliff. Well, actually, it's always going to be moving horizontally, so it's still got to be moving. Okay, let's say the question is, determine the velocity when it reaches the cliff height, which is right there. At that instant, it's got potential energy because it's got height. It's also got kinetic energy because it's moving. So a problem like this, again, same formula. Whenever you have a spring or a change in height, you got to go to conservation right away. It's going to be conservation automatically, okay? If you have just lateral motion left to right and no spring is involved, it's work kinetic energy theorem. That's that flow chart I put up I told you about on documents and handouts. That flow chart will help you to navigate when to use what parts. So what would this turn into? To start, you've got elastic energy. To end, you've got energy due to height. And you've got energy due to velocity at the end. Depending upon what you're given, you could solve for something else. Every problem is different, though, after that. But this is the key point right here. If you can do this, you seriously shouldn't be getting anything wrong after this point. Now it's just plug and chug. All you got to do is plug in your formulas. Clearly, you need to know what everything is, right? You need to know what's K in the problem, what's X, what's YF, what's the mass, what's the final velocity. Does mass cancel in this problem? I heard no. Why no right away? Why no?
There's 3 terms and one doesn't have mass.
Very good, Tiana. One of the 3 total terms does not involve mass. If they all have mass, you can cancel mass. I'm waiting for any of the questions. There's not really much more to say. We've been doing this for... Yeah, go.
I had a little bit of trouble with 93, I think was in the problem sets.
Anybody have the word problem in front of them any chance? Quickly, they can read it?
I have actually.
You do? Oh, yeah, read it. Go ahead, Jay.
A 65-kilogram bicyclist rides his 8.8-kilogram bicycle with a speed of 14 meters per second, and it's in 2 parts. A is how much work must be done by the brake to bring the bike and rider to a stop, and B is what is the magnitude of the braking force if the bicycle comes to rest at 3.5 meters.
All right, so let me quickly tell you what I drew right away. He said the mass of one object and the other object, so together what are we going to do with those 2 numbers? Okay, so we know the total mass.
73.8.
Okay, that's what we're going to start with for mass. Now, this is the initial velocity. What is it doing? Is it stopping or is it speeding up? It said come to rest. So it's stopping. So what's the final velocity? So I'm trying to find work. I've got a change in velocity, which makes me think velocity. What energy is associated with velocity? What type of energy is associated with velocity? Kinetic. And I'm trying to find work. Kinetic, work, kinetic, work. What theorem? Work kinetic energy theorem. So I go like this. I want to find the work done. I'm looking for the work. That's the final kinetic minus the initial. What's the final kinetic energy, everybody? How come? It comes to rest. So there's no velocity here. So it turns out that the work done is simply negative 1/2 mvi squared. That would be the amount of work done. Why is the answer negative? The object is doing what? What is the object doing? Its motion is either speeding up or slowing down. Slowing down. What is now, that's your answer. What is causing it to slow down? What is? The work done. What kind of work? Work done by? Friction. So if you want to figure out FF now, you can plug in FF times D times cosine theta. The D goes in right over here. solve for FF in that case. Make sense yet?
Yeah.
All right. Hey, please study hard over the weekend, guys. Okay, look at those examples, the extra ones in the text if you want. Look at the mixed review at the end of chapter 6. That might be a good space to find good examples. Okay? Practice, practice, practice.